11 said. No, it's fine. Yes, thank you. So we will continue our lectures in physics beyond standard model, and let me remind that we have 5 lectures. First one was overview of a standard model, and yesterday we had second lecture in 2 simple examples of possible extension of the standard model via a U1 prime, in particular U1b minus L. And I try to motivate this for you. And then also 2 hex doublets, because standard model 1 hex doublets, and then B minus L was 1 hex doublet plus 1 singlet. And it was very natural to consider also 2 hex doublet as a second step. Now we will go a little bit deeper in physics beyond standard model, and we will discuss simple group like SU5 ground unified theory. Okay, hopefully tomorrow and after tomorrow we'll have the energy and you will have the ability to listen for more topics like supersymmetry and extra dimension. Let me start with reminding you that in fact unification and unifying forces started long time ago in the 18th century when Faraday and Maxwell's succeeded to combine electricity and magnetism in one force. So before Maxwell, essentially magnetism and electricity was seen as 2 different forces, and then after that we understand that they can be unified in one force, electromagnetic force. And we discussed in first lecture even the quantum electrodynamics, the theory on the quantum level for these 2 forces. Then the story continued, and we studied weak interactions, and we mentioned the standard model that really weak interaction by itself was not consistent. It was non-renormalizable theory. It was not possible to make quantum field theory of weak interactions by itself, and we succeeded to handle the theory of weak interaction, and we combined with electromagnetism, and we have electroweak theory. It's a Lamb-Weinberg glacier that we discussed in the first day. In fact, as I told you, strong interaction was really somehow orthogonal, is not related to the unification of the electromagnetic interaction. However, it was very important to include it as well, even semi-direct product. And we have now kind of unification or partial unification for the 3 forces, strong interaction and electroweak. But the real unification with electroweak between these two forces. And as I said, we just add QCD on top of them, and we form the standard model for the 3 types of interactions. Now we really want to unify the QCD and the electroweak in the same sense of unifying electrodynamics and weak interaction in one real model, and this is what we will call it ground unified theory. So ground unified theory is different from the standard model. It is really deal with the standard electroweak and the QCD, but it tried to unify them in real words, not really just combine them like SU3 cross the electroweak. And they are just, as I said, direct product. They are just combined together for completeness, but not real unification. Here in the ground unification, we are trying to really have one source and one unified force to be split with at low energy to these 2 forces. So this is the aim for from ground unified theory, is what we usually call GUT. Remember, still we have a gravity. And in all time, similar to the magnetism and the electricity, we had this celestial mechanics, gravity, and terrestrial gravity. This was Kepler's mechanics, and this was Galileo. And then Newton came, said This is two versions. There is what's called universal gravitational force. The gravity at celestial level is the same gravity that we use at the terrestrial. So this was a Newton unification, similar to Maxwell's essentially. We have one gravity since that time, and then it is improved, and we have the general theory of relativity, but it still remains a gravity decoupled from the forces, the three forces, as I told you last time. So there's the aim also, but not the aim of the grand unification. Grand unification wanted to unify electroweak and the QCD, but our aim and our objective, our dream, also to have gravity unified somehow with the grand unified theories, because we failed to unify gravity with a strong or with a weak or whatever, because at the energy scale where this forces appears in that form, gravity is so weak. And we know that when we go in the energy scale, high energy scale, the unification becomes visible, and also gravity can be started to be more stronger and more relevant. So the hope that we will have somehow, compatible strengths of gravity at very high energy, and also we need to quantize it. We hopefully will have quantum gravity, and in this case, we can really merge gravity and grand unified theories in one theory, and this will be our underlying theory. This is the dream of having theory of everything. And string theory, one of the examples of this potential theories of everything, was really aiming to, but of course, this is very difficult and very ambitious step, and still string theory is not, it's still under construction, I would say. It has some very interesting features, but still not, we cannot claim that we reach it. Okay. Murad, do you hear me now?
Yes, I can.
Okay, sorry, the internet as usual was unstable. So I stopped, and I will start from where So did you hear my explanation for this chart, I guess?
Yes, yes.
Okay, so we can go to the second page or second slide. And I was mentioning that I think Georgia was the first one immediately after Standard Model. He was friend of the group of the Standard Model, Salam and Weinberg, and suggested that we may unify the three groups, the three interactions and three forces, the three groups, simply we call three groups. And in fact, we need to really know that to unify them in one fundamental force or one group theory to represent this unified force, you have to understand a little bit about the group theory of the Standard Model. So SU3, for example, this is the non-abelian gauge group, represent the strong interaction, and we know the number of generator in this is 8, and we call the rank of this group is 2, and the rank of this SU2 is also 1, is essentially n minus 1, and for the U1 is 1 rank. So the standard model has 8 generators, 3 from SU2, 1 from U1, so 12 generators. So 12 generators correspond, you remember, to 12 gauge boson, the gauge boson of the fields that we used to make a gauge invariant theory. So we need something bigger, or at least of the order of these 3 groups. Okay, so we are looking for some gauge group G with rank larger than or equal 4, and automatically, if it is of rank order 4 or larger, it will have the 12 generators and maybe more. So this is what the first condition you have to check when you try to select a gauge group to use it as a fundamental gut model that you try to. There is another criteria. This is just a matter of test now. You are not happy with SU3 cross SU2 cross U1 because there is no real unification, especially with SU3. Here, there is some unification comes from the breaking where you have electroweak 1 goes to down to electromagnetism. So there is some connection and so on. And as I told you last time, the neutral component, third A mu3 and E mu from here combined together gives Z prime and they give the photon. So somehow they are involved, but not unified completely. But this is completely, as I told you, side. So you need a kind of symbol group. You cannot have again direct product like this. Symbol group, like what we would consider today SU5, just one symbol group. Or if you fail to find symbol group, in fact, there is another big group, it's called SO10, but today we'll just give example of SU5. Or if you don't have symbol group, which would be useful or helpful with you to do the job, at least you can have some identical symbol group. So you can have SU3 cross SU3 cross SU3 or something like that. Try to simplify and try to have the 3 forces mixed together from this new. And another important, this is matter of, as I said, test and maybe for improving things, but this is essential, I would say. And the third condition is also an essential one, which that we have seen in the standard model that there is a complex representation. You remember psi and psi bar, and you know we have left and right, and this representation, fundamental representation in this groups was complex representation. So we need to keep this complex representation. Why not? Why not real representation? Because real representation will can I give you example for real representation like Majorana, like the right-handed neutrino when we added to the Lagrangian. This is Majorana, so it's a singlet. It's not. You can write mass term for neutrino right directly without any problem with any symmetry, and then this mass could be at very large scale. I told you sometimes people take it 10 to 13 GeV. So once you have real representation, you could have a direct mass term in the Lagrangian, and would be super heavy. Of course, your fermions, standard model, right-handed neutrino, we don't care. Can be heavy, super heavy, doesn't matter. But for fermions in the standard model, we need really to be sure that it remains massless from gut scales until the electroweak scale, and then acquire masses at the electroweak scale. So this is the complex representation is essential here to have a kind of chiral symmetry, protect your fermion masses. So Georgia and the people at that time make a kind of list of possible gauge groups that may satisfy these 3 conditions. Okay. In fact, the first condition, rank larger than or equal 4, you need to know a little bit about group theory. So that when I heard that in ICTV diploma, cancel the group theory course or something like that, I was astonished, because in particle physics, you need information really about the group theory. Anyway, so this is some example for groups with rank larger than. And let me just mention SU5, the last one. SU2 to power 4, simple group, but multiple of simple group. SU2 plus SU2 plus SU2 plus SU2. SU2, each one has one rank, so 4 times give you rank 4. SU3 squared, SU3 has rank 2 times SU2, SU3 again gives you rank 4. And there's some other, maybe some groups you don't have. This is orthogonal, not unitary, O8 or O9 and so on. And this, all of these groups are rank 4. Are of the rank 4. So all of them can be used. In fact, no. Why? Because look for SU2 to power 4, for example. Satisfy rank 4. Okay, satisfy complex representation, because we know SU2 has a complex representation, but it is simple groups, multiple of simple groups, so satisfy, but it doesn't really have any SU3. So it cannot accommodate the strong interactions. So you immediately cancel SU2. Same things for O or O5. So you need to be sure that it has. Take an example of SU3 squared. SU3s, one of them will be strong interaction, and the second will be like a weak interaction times the hypercharge. But in this case, the quarks, which is really, it should be in triplet, because SU3 is a fundamental representation of SU3 is triplet. Triplet, not strong interaction, not colored, not triplet under the weak. So from where? In SU2, we have up and down. So you need to complete this triplet with some other. So you may have up, down, and charm. Strange. In one multiplet. This will be your weak multiplet, because the SU3 weak now, not SU2 weak, which we call it SU2 left. Now this is SU3 left or weak or whatever. Okay, this is now good? No, not good, because this is guaranteed. Why I choose S? I choose S because I wanted the charge, sum of the charges in the multiplet to be 0, like what we do in, we will see now the sum over Q equals 0, which is required by the generators of this. But now if you have S from second generation, in one multiplet with a down and the up of the first generation, really you are violating generation structure. And it becomes generation entered in multiplets, and it becomes not very consistent. So that for that reason, this is not really option. SU5 really what remains as an elegant and viable candidate of rank 4. Okay, so why SU5? Really, people try to use rank 4, which is a minimal, and try to find any other group could help or could be used. And as we have seen, most of them have some troubles, and SU5 remains the viable candidate. Convinced? Not very much aware about group theory? Okay. Okay, now we will discuss SU5 means a unitary matrix 5 by 5 as SU3 and as SU2. And then the generator, as usual, will be extension from SU2 Pauli matrices to Gell-Mann matrices in the 3 by 3. And now I don't know what is this called, 5 by 5 generators. And as usual, remember, it's again, SU5 means the theory was invariant under global symmetry, but because you have multiplets, the fundamental representation, if five plates, the multiplet is 5 components. So this was same exercise we did with a global symmetry, scalar, not scalar, function psi or doublet psi 1, psi 2, or triplet psi 1, 2, 3, or fiveplet psi 1, 2, psi 5. At global is invariant, but when we consider local transformation, you need to introduce gauge. And the gauge depends on the representation and the psi that you consider. So you consider fundamental fiveplet, then your gauge will be a joint representation of this fiveplet, which will be 5 by 5 matrix. It's called a joint representation of SU5. And as usual, as we did in the SU3 or even SU2, we have AI plus tau I, now capital T I, the generator of the SU5. And the generator of SU5, since it is SU5, so the generator n squared minus 1, so 5 squared, 25 minus 1, 24 generator. More than what we want, in fact. We want just 12. But this is a minimal rank, and the minimal group contains SU3 plus SU2 plus 1. It gives you extra 12 generator. Is it good or bad? We will see. So now this is 24 generators, give me 24 gauge boson, and this is the way we represent it in this. Okay, what is a generator of SU5? Some work in group theory, you will see that they build it in the same way, by instead of Pauli matrices and Gelman matrices, you extend it to 5 by 5. So the simplest one, you take, like what we did with Gelman, we take Pauli matrices and you make 0, 0, 0, 0, and you extend it to 3 dimensions, and so on, and you replace it in different places, you get, and then one diagonal.
Doctor, so now, I'm sorry to interrupt you, but SU3 for the strong interaction.
Sorry.
I have some question to ask
you.
Yes,
please.
In the strong interaction,
yes.
SU3 group affect the color charge. In the electroweak, the SU2 left-handed affect left-handed doublet. The new one hypercharge affects the hypercharge. What the SU3 affect?
SU3 what?
The SU3 in the strong interaction affects the color charge.
Yes.
Right. What is the SU3 affects? SU5 in the gradient
SU5.
Okay.
Okay, just bear with me a second. SU5, we will decompose it again to SU3 plus SU2 plus U1, and we will see how each group and each force will work under SU5. But if you wanted to talk about SU5 in large, there is no color, there is no left-handed, there is no hypercharge, there is no up and there is no down. It's just wait for a while, because at this scale, all these groups, all these forces that we know about is not exist yet. It's part of fundamental force that we call it SU5. And SU5, when we break it down, let me simplify it to you. Electroweak and electromagnetism. At the electroweak scale, you have SU2 and U1 hypercharge. You don't have electromagnetism. Nothing is called electromagnetism at this scale. Above electroweak scale, above 174 GeV or whatever, there is no electromagnetism. There is hypercharge, which define the multiplet. And the multiplet is called the Q. We don't separate in this level up and down. They are just one unity, is called the Q, because at this stage, the particle really, let me also tell you, at low scale, we have proton and neutron. They are identical. If there is no electromagnetic field, there is no difference between proton and neutron, essentially, with some approximation. Proton and neutron will be identical. For that reason, we combine them in one multiplet, and we call it isospin multiplet. So the idea that different particles we see at different scales is not the same things you can see at higher scales in different pictures. So similar to isospin proton neutron, once you open the electromagnetic, the isospin multiplet is split to proton neutron. The quark multiplet Q has up and down. Once you break the electroweak, up and down will be splitting to U and D, and you will have charge minus plus 2/3 and D minus 1/3. But before that, they both are components in one particle content is called Q. And this Q, nothing to do with the charge, because it has two particles in principle will have later on different charges. So now SU5 will be, for example, 5-plet, big multiplet, super multiplet like this, contains quark and it contains leptons, but at this stage, there is no quark, there is no lepton, there is something called 5-plet only. And another multiplet is called 10-plet only. So I want you to, when we build now bigger group, you have to be open-minded to accept that the particles that we know will be part of bigger multiplets and will behave as a common multiplet, and later on when we break, we get what we know. Is this answer your questions?
Thank you, sir.
Okay, okay. So those are the generators, and as I told you, very simple to construct them. And then we have also very important generator, which is diagonal generator, to guarantee some generator of the hypercharge, which is common for all multiplets, for all multiplets. So this will be, for example, usual hypercharge, but normalized over 3/5. And there are another 12 generators created in different positions of sigma 1 and sigma 2. This is just mathematics. And we have 24 generator, and we will have 24 gauge boson. Now, the gauge field NU, which is in 24 representation, as I told you, a joint representation. In fact, not only the gauge field NU, any 24-dimensional adjoint representation, because we will use some scalar 24 representation as well, or if you have fermion 24 representations, it's just a representation. You can use it for gauge field, you can use it for scalar, and so on. It depends on the index NU or phi, or because the representation, as usual, there is a scale, the space-time, which you say this is vector, or this is a scalar, or this is a spinor. This is Lorentz transformation. And there is SU5. Is it 24 or 5-plet fundamental representation, or adjoint representation, or other representation? So don't relate or don't link the 24 representation only with the adjoint with a gauge field. In SU2, we have triplet representation, which is a gauge field, because we have the same AI times the tau I give you the gauge field, and this is a adjoint representation, which is a 3x3 made from W plus, W minus, and Z. But we could have triplet scalar, because there is no, in the standard model, there is no triplet scalar, but in principle, we could have triplet scalar, or triplet fermion, or whatever. So the representation is something which showed the transformation of this object under the group. And the spinor, scalar, vector is something else which show the transformation under Lorentz. So now when I said gauge field, I mean mu, and mu means vector under Lorentz transformation. And then I said it is a joint representation, 24-dimensional adjoint representation. This means it is like 5x5 matrix. It transforms like matrix form in the group SU. So the 24 representation in general it can be decomposed, as I told your friend now, that we need to really decompose it under SU3 cross SU2 cross U1. Because at the end of the day, 24, I will not continue working with 24 because SU5 will be broken down. I need to get the standard model and I need to open this box of 24 to see which one belongs to the standard model and which one is extra new gauge proposal. So the representation in this format is, you know, it's is divided like 8,1. 8 is under SU3, the representation under SU3. So it is a joint representation of SU3 is 8,1. And let me go to the big one, 1,3. 1 means what? Singlet under SU3, and 3 triplet under SU2, and 0 hypercharge. So we put the hypercharge subindex. So this is 8 is like a joint SU3, 1 singlet SU2, and 0 hypercharge. So it looks like 810 is perfect for the gluons, for the joint representation of SU3 gluons. And 1,30 is perfect for W plus W minus Z, the joint representation of SU3. And there is a singlet 1,1, okay? And there is 3,2 and 3 bar, 2 with hypercharge 5/3 minus 5/3. Those are certainly different and new. Why? Because those have triplet under SU5, doublet under SU2. So they mix SU2 and SU3.
Triplet under SU3.
Triplet under SU3, doublet under SU2. And they have some hypercharge. And this is anti-triplet, doublet, and so on.
I think you should take 1/2 plus that is 1/3.
Sorry.
Minus 5/6.
Which one? This one?
Yes.
For hypercharge? It depends on the convention. Yes. Yeah. So we could have 8 gluons here in the 24. We could have the 3 generators or 3 W plus minus Z0 S2 in 24 from this part. And you could have U1 hypercharge singlets like this singlet everywhere, singlets. This is engaged bosons, maybe not playing very crucial roles, but in the scalars, when you try to break some symmetry, usually you go to give the singlets some VEV, because singlets means SU3 singlet, SU2 singlets, hypercharge 0. So this is perfect to give it 0, to give it VEV. So it break SU5 and save SU3, SU2, U1. And this is what we want. We want to break it down to SU3. So this singlet will be quite useful when I consider what 24 scalar, not 24 adjoint. I never give vacuum expectation to vector. Adjoint representation mu that this is a vector. Why I cannot give the vector to the vector? Why it should be scalar? Because as I told you, vector means it is Lorentz, and then you break Lorentz. If you make a vacuum expectation value for vector, then you break. It is a charged under Lorentz. So, like when you have a charged part, a charged. Why in the Higgs we give the vacuum expectation value for phi 0, not phi plus? Because if you give the vacuum expectation for phi plus, you break the electromagnetism and you violate the charge. Here also, this is charged under Lorentz transformation, so you cannot give the vector or a spinor. The scalar is a singlet under Lorentz. You remember when they taught us the transformation and so on. The scalar by definition is invariant under Lorentz. So singlet in our terminology is singlet, and then you can give it a VEV, and Lorentz is saved. So this is 110. We are happy with this. And when I break SU5 2 SU3 cross SU2 cross U1, I have to go 24 scalar and give them to 1, 1. But here now I am talking about the gauge field. So this will be like just singlet gauge field.
So excuse.
Yes, yes.
So you mean the whole invariant impulse transformation is a scalar fields because they are neutral? They have in charge electric charge or
No.
hybrid charge?
Scalar charging. But this is singlet under Lorentz. Singlet under Lorentz means if you apply, you know how how the vector mu is transformed under Lorentz. Mu prime goes to what we call it sometimes lambda mu nu mu. So this is a transformation of the vector. The spinor psi goes to some Dirac and relativistic, goes to some S of lambda, some matrix S of lambda to take it to psi. So psi prime equal S of lambda. Phi, charged or not charged, phi prime equal phi. That's it. So this means invariant under Lorentz, singlet under Lorentz, and I can use it to break any other symmetry, charge it under this symmetry, and keep Lorentz invariant as it is.
We have those it's not charged as it is invariant.
No, I know Kabito.
Yes, it is not. Here we don't mean real charge, electric charge, something that we have in.
No. We use charge in large definition.
Yeah, in
So-
the context of symmetry.
Of the symmetry. When we said phi 0 is zero charge under electromagnetism, but it is charged under left-handed SU2 left. So when it takes a vacuum and it charges under SU2 left, it breaks SU2 left. It has a hybrid charge, so it breaks it is a hybrid charge as well. So it depends on the definition of a charge here. We mean charge under. Even Lorentz, we can say the vector is a charge under Lorentz, spinor, and the phi is a singlet under Lorentz. General definition, yes. So I just wanted to make a comment about 110 as a very important component in the 24 representation. Imagine if we do not have in SU5 representation 24 or 5 or 10 or whatever we will discuss, singlet like this, then there is no way to break SU5 down to SU3 plus SU2. So having component which is a singlet under SU3 plus SU2 plus U1 is essential, because once you give this value, SU5 will break down to 3 to 1. Yes, please.
So if we have a vector, can we contract it and we find also the
you will have a sector scalars from mu in nu, for example, but this is not fundamental scalars and blah blah blah. You know, before Higgs is discovered, people was trying to say Higgs is composite from two fermions. Two fermions, top, not our top, but heavy top bar, and make what's called condensations. And from this condensation, we can have, yes. In fact, in QCD, we have condensation from UU bar. This is a kind of chiral symmetry breaking. UU bar, yes, you have a spinor, UU bar, get a wave together. So we deal with them as a singlet scalar from two fermions. Yes, in principle, yes, but this is not fundamental. 110 will be kind of fundamental component of the scalar that we need. Back to the gauge field, the SMU, our 24 representation. I showed to you that it contains our 8 gluons and our SU2 and also U1 singlets hypercharge, which could play the role here, could play the role of the P mu. Remember, in SU3, we need 12. 8 from SU3, 3 from SU2, and 1 from the hypercharge. So this is when, and of course, B mu should be singlet under SU3, singlet under SU2, and of course, like photon is not charged under itself, its symmetry, so it's 0 hypercharge as well. So this will be perfect for B mu. Okay, so we have all our 12, and we have another set, another 12 crazy gauge bosons couple SU3 plus with SU2. We call this new gauge boson as X mu and X mu bar. Okay, and this X X, Y, there's a 6X and it's SY. X, Y are charged under SU3 and SU2 groups, means SU5, there are new vertices connect quark and leptons together. And this is somehow danger, as we will see. And this type of particles, which relate quark and leptons in one vertex, we call it leptoquark, because it couples not only with quark, not only with lepton, but both, leptoquark. And this leptoquark usually create a problem of baryon number violation, and in particular proton decay. And we will see one of the main challenge of SU5 is the proton decay, okay? Because this new generators, this new gauge boson. Any questions so far? Okay. Are you with us? Because I am not.
Yes, I'm here. Yes.
You are there. I have to open the video to see you, or what I should do? Let me open. Yeah, now I can see you. I cannot see the screen. Okay, where we are. Yes, so now this is simple. Try to write the 24. I don't know who asked it. Yes, one of the colleagues at online. The 24, instead of having unknown components, now really we can write the 24 in terms of the generators of SU5, SU3 standard model. So we wrote it in terms of the gluons, G, I, J, and the B for the hypercharge. And since B in the hypercharge is giving everybody charge, so usually B on the diagonal, as you can see, and also W3, W plus, W minus, X, Y. So this is a 24 representation, which is 5 by 5. It is symmetric. So I don't know how 24.
So between the diagonal and half of the anyway.
Sorry?
The contribution will come from if it's symmetric from the diagonal plus half of the diagonal.
But because it is concrete, I think X1 bar, X1, X bar, X2 could be different, because we have to count it as a 3 and those as a 3. So 6, 3 plus 3, another 6, 12. So the 12 are not symmetric. I said symmetrically mistake.
For example, X1 bar, can we just change the sign?
No, because we defined here X. It's complex conjugate. It's X mu and X mu bar. So this is coming from the generator 13 minus I 14, and this is 13 plus I 14. So it's like ZZ bar.
Yeah.
ZZ bar is independent. You cannot say they are dependent.
Yeah, but I mean, like, if we know one of them, we can just change the sign of the I.
However, you have to deal with them at the 2 independent degrees of freedom. Okay, because it's X and Y, not just 1 degree of freedom. So here is the components with a 24 gauge boson, and as I told you, usually we define the covariant derivative. So the one asked about what SU5 will do, what is the force, what is the charge? There is a color, there is left-handed, there is a hypercharge. Nothing here. Here we have just the gauge coupling is called G. It's represent SU5 force. You call it color, you call it super color, you call it just SU5. You call it just SU5. And SU3 was having coupling is called GS. Electroweak, we call it G prime or G2. And the hypercharge was a G prime. Now we have G. And the covariant derivative over the psi phi, if psi phi is a fundamental representation, means column, like vector, you act like psi1, psi2, psi3. We act with d mu. We said, okay, this will be like partial mu psi, the component psi b, minus this vector has a 2 indices in SU5 because it is 5 by 5. So this is like I and j. Okay, it will be pq times psi q. I think you are already familiar. In fact, in gravity, if you study gravity, the covariant derivative with Christopher Sandler is even. In fact, the A mu is it's called connections. In fact, in the language of the gauge theories, because when we study gravity in gauge theory notation, we call it connection, and it will play the role of the A field. So this is a connection or the A mu. You apply the covariant derivative in very similar way. What's this chi BQ? When we have not fundamental representation, but some other representation like what I will show you now, the 10. There is a 10 and the 24. Comes from where? Comes from the multiplication of 5 times 5. When you multiply 5 times 5, back to 2 times 2 to learn how to get it. 2 times 2. Usually you said 2 times 2 is very simple. Either you multiply 2 bar times 2, you get singlet, just one scalar number. Okay, this is what we call. And you have another way to multiply 2 times 2 with epsilon ij. You get triplet. 3. So 2 times 2 has a symmetric part, which is 3, and anti-symmetric part, which is 1. So 2 times 2, 3 plus 1. This is a multiplication. 5 times 5 is in fact 24 plus the anti-symmetric part is 10. So you could have 2 fundamentals, you multiply, you get higher representation is 25. And the 24 is even higher representation from 5 times 5. So the 10 will be like chi BQ, but B with Q, B is 5 runs from 1 to 5, Q runs from 1 to 5, but anti-symmetric. You remember also in general relativity, you know, usually when you have indices, PQ, you make like bracket like this. So called B, when B equal Q is 0, Q equal minus QB. And this is will reduce the degrees of freedom to 10 in the case of the anti-symmetric. You multiply, you get the matrix, you kill the off diagonal, you kill the diagonal, you make the off diagonal anti-symmetric equal minus sign the other diagonal. So you get only 10 components. Okay, so this is a 10 representation which come from 5 times 5 anti-symmetric. 10 times 10 has a 2 indices. The first Q comes from the first 5, and the second, so B comes from the first 5, and the Q index will come from the second 5. And the anti-symmetric, you have to take it into account. When you multiply or when you act on this 10 or whatever second rank tensor now, or second rank, we cannot say spinor or whatever values, you can chi BQ act, D mu act of this will have similar to general relativity 2 connections, and with changing the indices in very particular way. Yeah.
So will be included like the case of U1 electromagnetism and SU2 and SU2 left and the U1 hypercharge, like it doesn't see it in the larger scale. It's the same here. Like here we don't see the color or the
we will see it only when we break SU5. And you will see now the 5 I'm talking about. But before going to the next slides, any questions here? Seems no.
No, not problem.
Okay. To make you're puzzled more and confused more. The 5 blades in SU5, you need to choose it in a way, especially the fundamental 5, because it will act the hypercharge, the diagonal generator will act on n, and it should really, the sum of this charges should be 0. So you will discover, you can convince yourself and easily to find out that the 5-bit, how I can construct the 5-bit. I'm talking about the spectrum now. I will not add, stones and whatever in the 5-bit. I don't have more than quarks and leptons. This is my fundamental spectrum in a standard model that I wanted to
Doctor, there is a problem in the words. Doctor, you are mute.
Sorry. I always forget it. So now we continue with the matter, unification of the matter in SU5, and I was telling our colleagues here that we need really to implement our standard model fermions, quark and leptons in this multiple of SU5. So it turns out that the 5-bit will contain the quark, down quarks, and positron and neutrino, anti-neutrino.
We can see the identification scheme of the SU5 that works in the indistinguishable.
Exactly.
And like in the scheme of the SU2 cross U1, the electrons and neutrinos are indistinguishable.
Unless you break, then you have electron and then you have neutrino. The example I mentioned about the isospin is exactly the same. Once you break by having electromagnetic break means it's not really break. You turn on some interactions which distinguish between components. Then you started to have electron and neutrino. You have proton and neutron in different shape. Here also, once you are at high energy scale and the SU5 is a common force, then the quarks down with the electron and the neutrino all in the same model. And then, as you said, all of them are really non-distinct. And this is now give some immediate important result that since the electron and the positron, we know the charge very well, then the down really should be to have the sum of the charges of this model to be 0, then the down should be really charged minus 1/3. So this is one of the good results that we started to understand about charge quantization in SU5. The word charge quantization in standard model or below standard model is not really defined. There's no way to explain why there is a charge quantization. But here it's clear that we have 3 quark with the electron and with the neutrino, and the sum of them is 0, so the charge will be 1. Yes.
So you see that as a consequence of the SU5, we were able to explain the minus 1/3.
Yes, yes. This is one of the advantages. And then the anti-phi star, emission conjugate of phi, will have the same conjugate of the same field. What is the up? We have only down, and we have only electron. Of course, this regeneration, you will have 5i, and the electron here is just representing the generation. Okay, so electron beyond tau depends on the I. You can just remove this L plus, E plus, you can write it as L plus I. And this is right-handed because we have anti-neutrino, but it is essentially left-handed. So still we don't have really right-handed neutrino. We have just left-handed neutrino, and it's a Hermitian conjugate, which is not right-handed. So this is now the pilot. What is the up? We discovered that the up sector really can go in the 10, the adjoint representation, not the adjoint, the representation, which is anti-symmetric 5 times 5 that I was talking about. And this is now contains, in fact, the up, and also again the down is E plus, so it is kind of, because it's 5 times 5, one of them is really up, and one is really has a down electron, and it has this structure. So it's possible to do some exercise, and I hope someone will complete the notes as we agreed. If we will not give you new tasks, but at least the task is that the lecture. Oh, by the way, all the lecture and the video I sent it in the Dropbox. Did they share it with you? Okay, I'll ask Shoaib now to do, because the first 2 lecture slides and 4 videos, and this is I will do. So please try to make a notes with the comments that with your questions and the comments and so on. It will be much more comprehensive than this. And as I said, each one will do notes for 1 lecture. This will be good for all of you. Okay, so up and down is transformed.
Still down.
No, because the charge will not be conserved.
So we also
Because conservation of charge is related to the conservation of the hypercharge, because Q is hypercharge minus T3 essentially, and in the diagonal you have T3 is the same.
And it will have to hold it, while below it didn't
I understand, because this is just the charge conjugation, and I think if you multiply, if it is had a sign, I understand your point. It depends on how you define the charge. If it's 5 star, just you take the complex one, or you multiply with tau 2, which is sigma 2. But I think here you take just the 5 star. So okay, this is it. Now, with these components and these fundamental representations for that, we can go and look at the interaction, gauge interaction. You remember the d mu psi b or fundamental representation, d mu 5 or d mu, not d mu 10. You will act d mu 5 and d mu 10. So acting on d mu 5 and d mu 10, this is what it creates. Remember, I told you d mu, it had partial mu plus the gauge mu, which is 5 by 5, which contains all the g's, all w's, and all x and y and all this stuff. And you multiply with 5, which is down, and the electron neutrino, or 10, the one we have seen. Yes. Yes.
On the screen. Okay.
Because can I see the audience without making the video? Because we need to save bandwidth as well, but I cannot see them if I stop there.
But also,
no, but at least I can see on. I don't know. I'm not expert in Zoom.
it still says if you have the camera on, the connection is still poor.
Yeah, this is what I am saying. Yes, let me stop the videos, but it disappeared. How I can make people online? I think you can see people online. No, the people online. Sometimes we see the people online on the right-hand side or something on side. I don't have it.
I can see that.
I think it needs to click on something. Enable this, I don't know.
Maybe open the camera and close it again.
I did open the camera and
Close it again.
I did and it disappeared.
On the left side of the
Yes, yes. No, this is will show you the list here, not look if we anyway, we don't want it to waste. If I open the camera, you see this is will show this. It will disappear. It will disappear. Anyway, so back to the Lagrangian. As I told you, you should, in your notes, you should take the 5 by 5, the matrix. There it is. This one, but remember, partial mu is multiplied by identity matrix 5 by 5. And then minus IG, this mu. Then you have all this 5 by 5. And then you apply the covariant derivative, partial mu psi. So this is will give you simple. And now we are interested in the second part, a mu psi. So this is multiplication, 5 by 5 matrix times 5 by 1 vector. And you collect, but this is the d mu psi. In the Lagrangian, you have a psi bar, d mu psi. So you have a psi bar, d mu psi, and you collect now all the singlets or the multiplying things. You understand me. So now you will get this terms. For example, you will get this term where you have a gluons act between like kinetic term, kinetic action, yes, d bar c l gamma mu gluon g mu lambda dc. This is SU3. So this is gauge coupling. You see universal gauge coupling now for all. Remember, when SU5 is broken, even G will be split in GS, G2, G1. And this is now the interaction. From where this comes from the part in the 5 by 5 mu, which contains a G. You collect all the G's multiplied by this kind of T bar D. And then you have W between the leptons. And you have the U1 interaction, for example. Remember, I take the 5. So only D, electron, neutrino. D will interact with the gluon. And electrons will interact with W. And D also interact with the hypercharge. But DCl, this is a complex conjugate of DCl, which is D right. So D right has no W interaction because this is right. Usually we work either we call it D right or DCl, but you have to be sure that you are talking about the thin fins, which is a singlet under SU2. Therefore, we don't have any interaction with that, but interaction with hypercharge. And now we come to this new interaction. D with the electron via X. D with the neutrino via Y. This is the two generator or two gauge bosons, the new gauge bosons that we were talking about. Link down to the electron and down to the neutrino. And once you have coupling like this, you have to worry too much because the proton could decay, as we will see now, via this type of interaction. Let us continue and consider the gauge interaction with the 10. So I have chi bar, a mu, partial mu, whatever, act on 10. Okay? And then I can continue this now from the 10, since the 10 contains U and D. So I can have a strong interaction, UU bar with the gluon, DD bar with the gluon, and again lepton with W, not leptons, up and down, because this is left-handed. I have to remind you that 10 has a left-handed down. Here it has a right-handed down. So the down U, because we have D right, D left, U right, U left, and you have lepton left, E right, no neutrino right. Okay. For that reason, in this one, we take it 0 because the neutrino left is taken here. Okay. So this is now left for down, which is different from this down, which was right. And here's UC, which is a kind of U right, and U, which is kind of U left. Okay. So everything is included in the 5 and the 10. It's enough to describe the standard model with these two representations. By the way, 5 and 10 is not the only representation, and we consider now 24, 5, and 10. And we said 5 is the fundamental, 24 you could have it from multiplication of 5 times 5, and the 10 also you could get it from antisymmetric multiplication of this. But there is more representation we will mention right now. Yeah.
So here's a BMU represents
vector which BMU the hypercharge.
Yes, the hypercharge.
Yes.
For here is so here you want
yes. No. I'm just saying electromagnetism is down the end. We are talking about SU5 and how we wanted to have a zoom to see SU3 cross SU2 cross U1 hypercharge of the standard model within the SU5. So that we have to do it carefully to guarantee that all interactions are there. When we break how to break. When we get some stupid interaction like this, we create problems. When we have a representation, we have to be sure that there is a singlet that we can give it a VEV and break the symmetry down to 3 to 1. So this is like, you have SU5 and you are trying to check 3 to 1 from it. If you talk about electromagnetism, you cannot see it in SU5 at all. This is the third or second order approximation now. Okay, so I showed to you that 10 and 5 create interaction via X danger interactions, in fact. Now, before talking about the danger interaction or whatever, we need to discuss symmetry breaking and Hex mechanism here and how to break SU5. I already mentioned now we have some singlet component in the 24, so this is perfect. By the way, 5-plet has no singlet, 10 has no singlet. It's just, we will see the decomposition of this soon. So the best way to break SU5 down to standard model will be via the 24. Why? Because the 1,10. But now we have to consider some scalar field capital phi. This is what we call 24-dimensional adjoint representation, scalar, not vector. So I made it clear that the vector and the scalar could have the same representation, but they are two different entities. Now, we need to break SU5 at high scale down to standard model SU3 plus SU1. And I think now you are convinced that this can be done by Hex in the 24 representation via the last components 1,10. Okay? Like the doublet in the standard model, where we have phi plus, phi 0, we do it via the vacuum expectation value of phi 0. Then we break it down to U1 electromagnetism. Now we will do it via 24 and only singlet 1,1. And 1,1 in 24 is a kind of element on the diagonal because this is not 5-plet and you will have 0, 0, 0, 0 V. This is 24. And the singlet here 1, 1, 0 is really the elements on the diagonal elements. So this is the vacuum, we'll take the vacuum expectation value on the diagonal. So any components on the 24th in the off diagonal or in any part of this will break immediately the standard model as well. So you need to be careful. You give it here on the diagonal like this one, satisfy that the sum should be 0. There's V missing here. So V minus 3 over 2 V minus, because this is 5 by 5, not 4. So this is what we mean, because singlet in doublet was just 0, 5, 0 V. Because a doublet is a fundamental representation in 2 components, and singlets here means a 0 and a V. In 24 representations, this is 5 by 5. Singlets means you give the diagonal element there. So you break it with the 24 with this verb down to SU3 cross SU2 cross U1. Perfect. And then you take it down to electromagnetism, and SU3 should remain exact via some doublet, and this is at electroweak scale MW. So we will have 2 steps of breaking. One to take SU5 down to the standard model, and one from the standard model to the electromagnetic field. Not standard model, you understand me, standard model means electroweak strong force, and then you break electroweak down to electromagnetism.
Excuse me.
Yes.
So here's this 5 to 5 matrix represents one singlet or a 5-tone.
No. When you open all the elements in that way, remove this vacuum substitution now. 5. If you take 5, capital 24, how you will write it? You write it 511, 512, 513, 515, and then 521, 551 until 55. So this is the complete 24. Okay. Now this 24, this whole element, I showed you that it can be decomposed like 8, 1 and 3, 1, 3. And there is 1, 1. So this means what? This means you remember, if I take the first 8 elements here, I take it and let all the other elements zeros, and the sum plus, you take the 8, put 0 in front of it. Decomposition. This is a decomposition. So you take block and the other parts is 0, and you take it out plus. The block you take it, put it 0, you keep the second block and it's 0, and so on. So you decompose. One of those blocks will have this diagonal. So the diagonal element you separate it by itself. This is the 1, 1 we are talking about. And this is what we will give it back. This value will be in this form. Okay? First time to hear about SU5, so it's good you don't expect to understand 100%. Otherwise, you will not make the notes. You have to make the notes. So the scale now of MX should be quite large. Why should it be quite large? Not just, for example, above TV, because the MW is 100 GV or so. Well, I agree with you. I don't like to just give you impose the information on your head. We said 10 to 15 or gut scale or whatever. We will see that there is a necessity to have it at 10 to 15 GV. Why? First of all, the X and Y will have mass from this VEV, and they are danger. So you need to push them very, very high to avoid proton decay. Even with 10 to 15 and or so is not enough. Second, you will find that the whole game here to have a unified things. SU5 is unified force with 1 gauge coupling G. So you really wanted to show that G1 and G2 and GS, when you go and you run to meet at some point with one single value, what we call it G in the SU5, you need to go up to very high energy scale, up to 10 to 15 or 10 to 16. So the vacuum expectation value, which started to break the G down to 3 Gs, should be of that. We will see this. Yes.
You see that SU5 at this very high large energy. We have a proton decay. Below that, we don't have a proton decay, right?
Yeah, because below that, the X and Y are decoupled.
Yeah, okay. So it's just an attempt to explain the
unsuccessful attempt. It was an unsuccessful attempt because still proton decay is 10 to 32 years Less than 10. So even 10 to 15, just to give you the border, and it's not enough. So, and then standard model would be broken down to, you know, the scale of symmetry breaking. Usually, we don't really predict it, but we motivated. Why verb here 174? I told you last time it was essentially in the standard model free parameter. We fix it from the G Fermi and the relation with mass of the W. You get W, then you get the verb. And then when you get the verb, you predict the Z, and hey, yes, it's good.
But the G Fermi was really
Observed experimentally, yes. So it's not really, the V is not predicted theoretically. Okay, it's 174 is obtained to give you the MW 80 with a gauge coupling that we know. And you know that MW is 80 from the G Fermi and from the measurements of the low scale, low energy Fermi and the nuclear and
so this case it's
the MX is theoretically, and it can be anything. And then we try to use the gauge coupling unification and the proton decay to put some limits in this. In SUSY, it do some helps to tell you where this, but still it's not cut prediction. Yeah. Now, after you need two hexes now, MX hex and MW hex, and of course MW hex should include our hex in terms of SU5. It should be contains our doublets. Our doublets, the one we familiar with, which is 0V, but this should be inside 5-plate. Okay, just simple. The 5-plate, as I showed to you before, 5-plate can be written as, yes, hey, the 5-plate can be written as a triplet plus doublets. So this is easy. You can see the 5 components. You can take the first 3 separated in the way of the compositions that we mentioned, and the last 2 take it as a 2. So this is 3 plus 2. Okay, it's not just in simple way like that, but this is really the. So 3,1 with a hypercharge 1,2 with a hypercharge 1. This is the separation of the 5-plate. So the 5-plate, it has 5 components. 3 of them we call it triplet, and the 2 of them down we call it doublet. Our standard model hex will be in the doublet, will be in this capital H as a last 2 components, and those will get vacuum expectation value to break SU2 cross S cross U1 at MW, and in normal way to give it VH. Okay. How to guarantee that this is 0 and this is only will get there? Okay, we will adjust the minimization like what we did in the standard model to have the 5, the element in the H5 plus our first component to be 0 there. The second component, which is neutral, takes only the there. This can be adjusted, no problem about that. But you have parameter in the potential, you can adjust the M squared to be negative and blah, blah, blah. So, but in principle, yes, the triplet will be with 0 there, and the last component only will be with a vacuum expectation value. I call it here VH, just to show that this is a standard model. Okay, you see the parameters. VH will be pushed to this factor, and then that will be G squared and VH squared, like what we obtained in the standard model.
So here is a potential. In this case, we have 2.
The potential is here.
Yes, yes, we should have 2. We should have 2 minima.
But look, the 2 minima. If you are, this is 2 different fields. So I could imagine that I have potential is called V of phi, comma H. Now I am talking about V of phi independent of VH. So V of phi is a 24th, the one we said diagonal. So V of phi is in separate from the V of H. So this has a minima and this has a minima. So when you plot and you said 2 minima, this is 2 minima, you plot it if you have just one axis, or when you have just one field, but this is 2 different fields. So you plot each potential. You could have also V of phi comma H where you have some interaction term between phi and H. But this will not play a role in each. This will be like interaction later on. And when one get a VEV, then generate mass for the other and so on. We will use this now to solve some problems because this hex, the triplet, this is a triplet and it is in the 5-plet. So really, again, but before going to this, I will discuss the unification. Okay. So I told you that the scale of the Vx or the vacuum expectation value at Mx should be rather heavy, of order 10 to 15 or so, and motivated by two things, proton decay and the gauge coupling unification. So in fact, in standard model, if you take just the standard model and you run the gauge coupling, you will never find that they meet in single points. They are not unified. However, this simple normalization group equation, okay? I hope if you never did it before, do it once in your life. This exercise for RG of standard model, and then this exercise, I am giving you the RG and all the coefficient here, and then you repeat the exercise with the SU5. SU5 will take you, it's modified hypercharge normalization, and also change some beta function coefficients. So you take this and you run, and you see now they meet at some point. Exactly not that sharp point, because this is to have it really sharp at single point like this, you need supersymmetry with U. But anyway, they meet in single point like this at almost 10 to 15. Okay, and therefore we said the unification scale should be rather larger than or equal 10 to 15 GV. So if I have G1, G2, GS are separate and they met together only in the framework that I am considering that I have at high scale some SU5, I got at 10 to 15 GV. This means I have to have the scale MX 10 to. Then the proton decay comes to confirm that we need really to have this such large scale. As I told you, X and Y are really kind of leptoquark fields. So because it couples quark and leptons in one vertex. So I could generate, because I have UU bar with X and DE with X. So remember, the proton is like, proton is 2U, 1D, okay? So imagine there is a D here, you call this spectator quark, which is not just lying here. D enter and D out. So you have 2U and 1D, which is a spectator, will be the proton. And then X change 2U to E plus D, and you have a remnant, hence D. So DC-D give you kind of K meson and electron. So the proton will decay to K and electron. The decay, sorry?
So that we need to get this very high.
No. You know the mass of X. Okay, the mass of X, you call it mx, which is proportional to the vacuum expectation value of V. Why? Because this is a gauge boson coupled with capital phi. Phi got a VEV, like W mass is proportional to the mass is proportional to the VEV. So this will be proportional to the Vx, which is 10 to 15 or so. So you said, okay, I have it here, and also Y and all this can be calculated in this way. So you can calculate the decay rates proportional to 1 over mx to power 4. Okay, so if you, I know that you are thinking that this is done at, but when you have particle like this, effectively, this is proportional to 1 over mx to power 4. So you take mx with this 10 to 15 GV, and you calculate, you will find that the experimental proton lifetime, in fact, 10 to 34 now. I don't know. My last information was 10 to 32. But if I wrote it 10 to 34, so there may be updates. It's almost stable till the end of the line. And now this is require mx to be even larger than 10 to 16. So you said, okay, but I got it 10 to 15. Yes, 10 to 15 with a force power, it makes a couple of orders, 4 orders of magnitudes. So this is give you something of order 10 to 30 or so years. And in fact, this is not enough, it's violating the limits, because in Japan, they are making a lot of experiments to test or to check the proton decay, and it's so far negative result, and they transform it to this limit. So SU5, the scale is order 10 to 15, which is not really. Can we push it to 10 to 16? Yeah, it's not that easy, but you need to play in not minimal SU5. You need to go to non-minimal, and I will mention this at the end. Okay, the interaction and Yukawa coupling for low energy and standard model. So you need again to know a little bit about the multiplication of this multiplets. So we have 5 times 5, we easily said it can be 10 or 24, but now you need to also multiply 5 times 10, 5 times 24 when you have gauge interaction with the gauge. But in Yukawa, no gauge, so we just so 5 star, yeah, remember 5 contains hex, our standard model hex, and 5. Our down, right-handed down in 5, and the 10 contains up left, up right, and down left. So you need really to multiply, you need to combine some invariant Yukawa like this. So to avoid confusion between the 5 with down quark and leptons and the hex, we call it 5H for the hex. So you need always to have 5H because you need to have your own Yukawa, standard model Yukawa. So standard model Yukawa contains a hex, it's a standard model. Forget about the 24 now, 24 will give mass for X capital and will go to the head. Now we have this. Okay, fortunately, 5 stars times 10 will have 5 times 44. Okay, so need to start group theory to know how to get the 5 and 44 from 5 to 10. But once you have 5 and then you multiply by 5 star, this is 5 times a 5 star, like column times a vector, you can get singlet. So this is good for singlet. Forget about this is quark and this is hex, but the representation is 5 times 5. And when we are multiplying according to the group, we don't care about the content, matter, scalar, blah, blah. I want it to be singlet. Singlet contains some quark from here, some quark from here, and some hex from here. This is perfect. This is a Yukawa. This is what I want. Okay. Now, 10 times 10 times 5 can also give me another Yukawa coupling. Yes, because 10 times 10 is also have 5 stars. And then 5 stars times 5H will be exact. So this is the two things. Okay, and I can translate this multiplication and this group theory multiplication to our real Yukawa interactions. Like some coupling, you call it, we don't call it Y1 now because it's still at high scale, because still I am talking about 5 and the 10 and the 10 star. So I call it gamma 1, some coupling. This is the Yukawa coupling at large scale. And then 5, 10, 5 star. Gamma 2, for 10, 10, 5. This is the way how to get singlet from this 10, 10, 5. You use some epsilon and with how many indices? 2, 4, 5. Because there is 2 indices, 2 indices, and 1 index. So this is a Yukawa interaction at low energy after the electroweak symmetry breaking. Electroweak symmetry breaking will split the hex 5-plet to triplet and the doublet. And we are interested in the doublet. Hopefully the triplet will be rather heavy. And now I can get the down from here, down from the 10, and the hex, my hex from the 5, which will be proportional to the vacuum. And this is giving the mass for down and the electron. But here is quite remarkable result, because I got the down sector and the lepton, because they were in the same multiplet. They were with the same Yukawa coupling, with the same hex, got the same verb. They are getting the same mass. Okay, so from this result, I essentially get M electron equal MD, and MS equal M mu, and MB equal M tau. So lepton mass equal the quark down sector mass. Is it good or bad? We will see. And now the interaction from here is giving me just something for the up sector. In fact, this is at some high scale. If I run it down, high scale 300 GeV, because this is the vacuum of the hex 5. So running down the mass to the low scale, we get MB will be 3 times M tau. And this is good. So at gut scales or at high scale, above electron scale, I can have PMB equal M tau, no problem. But at low scale, I know that MB 4.5 GeV and M tau 1.7 GeV. So MB almost 3 times M tau. I can get it if I have, this is at high scale. But these two relations are very bad, because if I run them, I really do not improve it. And in fact, there is no at low energy relation like MS3 and MU, whatever. So the mass relation for light MS3 and MU over ME are violating experimentally. So this is another disadvantage, another problem faced the SU5. And usually when you go to SU5, I have to be honest with you, I'm fond of gut models and unification and everything. But when you combine all the quarks and standard model particles in one doublet like 5, and then SO10 in one doublet, which is 10, you will have a problem with these masses and this thing, because all particles was identically in one multiplets and have some coupling, and they are getting waves together, and then to separate them, enough to get different masses and different behavior at low energy becomes rather difficult. Therefore, the issue of masses and all this stuff in gut models is much more difficult than do it without gut.
Excuse me.
Yes?
Is this relevant
At high scale, yes.
Yeah, at high scale. It represents, however, it is wrong in agreement with experiment, but it represents the behavior of how the mass changes with our running with scale.
We hoped so, we hoped that it will give us good results, and then we have explanation like the relation between MB and C3 and tau. We understand, hopefully, the SU5 gives a nice why MB equals 3 M tau. We don't know, it's measured like this. But now, if SU5, imagine we don't have other 2 generations, we have just this generation. It's the 3rd generation. So SU5 is telling me that, okay, we have MD equal M tau at some scale, and the difference comes from the renormalization, from running from high scale down. This would be nice to explain why there's 3 times M tau. But unfortunately, for the 2 generation, it doesn't work like this. So the RG is blind, as RG is taking some high scale mass down with some factor. It doesn't really change this from this to this. So, however, because as I said, all of them was in one multiplet, all of them is getting the same effect of the hex, all of them was the same coupling Yukawa capital gamma 1 y1. It's expected that the relation will be tight. And there is big chance that the expected relation may be not consistent with experimental results. And this is an issue. You wanted to really get gut models and you break it, you give all this, which it's very difficult. And
so this is the disadvantage of the SU5 model?
Yes, this is what I'm collecting advantage and disadvantage. And all this disadvantage, as I told you, there is no single ground unified model, although the idea is perfect, is making good advantage, but it has some drawbacks. And they require, once you go from simple scenario, like SU5 with 5 and the 10 and the 24, this is a simple scenario. Then you start to add something else. I will tell you that we solved the mass relation by including other hex. Why I just use the 5? There is also other hex 15 and the 45, and then I keep some other hex with some other contribution to make different sector get some different. Okay, then you can, but it's not that natural. Okay, but we don't know. Nature is not. It's called natural from nature, but nature is not usually takes a natural way. Okay, we have another problem in SU5. And this is called doublet, triplet splitting problem. We have a triplet and we have a doublet in the same SU5, in the same 5-bit hex. Again, the default that they will get same mass, almost. You want your doublet of order electroweak, then the triplet will be of order electroweak. What will make that triplet heavier? They are in the same mode. Why you are worried to, why you don't want the triplet to get mass of order electroweak? Because this is triplet has SU3 color and SU2 interaction, because it was in the doublet, it was in the 5-bit, in the 3-2 component. Remember, let me remind you, the 5, when we decompose it, yeah. 5 is 3,1 with a hypercharge minus 1/3 and 1,2 with 1/2. Okay, so it has only hypercharge and the triplet SU3 and the singlet under SU2. Good. However, it couples. It couples with a quark. I called the 3 component in the H5 as a capital T, just to focus on the triplet part. So I call capital T. So you see it couples, since it has this 5, which couple 5, which comes from the you coupling 5 times 10 times 5H. Remember, we said 5 tens 5H. So you can have really either coupling and from the 10 as well. I should remind you with a Yukawa. Here is a Yukawa. Here is a Yukawa. This is what we call it 5, 10, 5. And 5, 10 here, it has a T and the H. And this has a T and the H. So you need to separate T and you collect the interaction. In your notes, if you will do any notes, you will find that the Lagrangian will be like that. You have triplet coupling with the part which we call it Y5 or gamma 5 or gamma 1 or whatever, the first part of the Yukawa interaction, where we have 5H with 5 times 10. This is what we call it. And then also from the 10, 5, you could have DU and the LQ. It's enough, don't continue. This is danger because it has QD, it has a Q lepton, quark lepton vertex. Then this triplet will be like leptoquark, like the X that we are talking about. So this T in principle will contribute also to proton decay. And X, because it is gauge coupling, a gauge boson, it has an interaction with a gauge coupling. So the gauge coupling is fixed because this is the value where the 3 gauges meet. Now we have Yukawa, but Yukawa also the same Yukawa used for the masses. You cannot put it 0. You cannot play. It is the same Yukawa which gives a doublet to coupling to the doublet with the quarks, which give masses later on. So this mass of the will be like y up and y down. The interaction here for the proton decay will be like Yukawa up, Yukawa down over mt square. Not even mt mx to the power 4, but mt square. So this is required again very, very, very large, at least 10 to 12 GVMT triplet. Something crazy because I have triplet in the same doublets 5. You want the doublets, the 4th and 5th component to remain light, remain 100 GV, and those becomes very heavy, super heavy, 10 to 12 GV. Any explanation to this? This is known as doublet triplet splitting problem. So you need to split the doublet from the triplet, and this is a problem. Okay.
Is this very high scale?
We didn't get. We have to assume.
Otherwise,
Otherwise, you will get proton decay. So this particle to propagate proton decay, the triplet. And you cannot, as I told you, you cannot forbid it by putting the interaction vertex 0, because this is the Yukawa interaction which gives the mass interaction of the Higgs to all the fermions. So you have to admit it. And then the only solution to this problem to push the mass to very, very, very high scale. 10 to 12, 10 to 13, to God, better, more scales, more high scales is better. But the problem now, how to explain? One multiple together, split it to very heavy and very light, essentially 100 GV in this case, very light. This is a problem, or this is a splitting problem that we are talking about. Any solution to this problem? In fact, no. There is a fine-tuning solution. They play somehow with masses of the H and the masses of the T, such that at the end of the day, T will be heavy and the H will be. Masses of H and the T comes from where? From the potential. And the H by itself get vacuum excited. T doesn't get any vacuum. T will be just affected by the vacuum of either capital phi, which is 10 to 16 or 10 to 15 GV, the one breaks the MX scale, or 5H or VH, which is 100 GV. It depends on who's coupled with who, and then it gets them. So they said, okay, let us consider the potential V of phi comma T. No, V of phi comma H. The whole potential, where we have V of phi, which will have a minimum at MX, and we will have V of H, which has a minimum at 100 GV, and then we have an interaction between H5 and phi 24. Okay, and then they allow phi capital to couple with a phi H. Be careful, because phi capital is getting their vacuum expectation value of order mx, and then it could contribute to the mass of the whole mh. That's true. But they said, okay, we will have the parameter like this one. We have we have it here. So we will have like 24H, the capital phi, we call it 24H. Then this is the one we'll get there. I will call it with a sum coefficient A. So this is phi H star 20 is invariant. Okay, so it's okay. And this is coupled with 24, and when 24 get vacuum of order mx, it gives this mass of order V, which is very. Are you crazy? This is will give you mass for the capital T, but also mass for capital H. This V capital and this V capital. This V small will be just the mass term for MH, like M square H square. Okay. And they said, okay, the mass term for capital T for the triplet T squared, this is a master, is 2AV over square root plus B. While the mass of H is minus 3AV square root 3 over B. I agree that you remember 24 from the diagonal, it has a V and it has two component, last two component minus 3 over 2. So when we give the 24 VEF, we have a V and we have minus 3 over 2V. And this is what makes the difference in this combination. So this is the reason why we have minus 3 here to absorb, and we have here factor V on it. But is it enough? Still, this is V, M blank, M gut. And this is V, apart from positive or negative, even you make it worse if it is minus with V, and B should be now of order MX to absorb this minus 3V and give you something of order 100 GV. Can you imagine? I want to cancel 3 times 10 to 15 GV. And I get just 100 GV. This is even fine-tuning probably more than the cosmological constant. Sorry? No, but if A is small, you will suppress the mass of the T. A here is the same A here. So if you want T to be gut, take A equal 1. If you want T to be 10 to 12, take A 10 to minus, I don't know, 3 or whatever. But this will still give you this value equal almost to this value, but you have minus sign. And then the point, oh, I have a B here. Could I have it also of order V? And then I subtract it or of order 4 plus 4V. Not 4 plus 4V, you will end with 1V. Then we wanted minus plus 3V plus 100 GV. So plus 3V cancel minus 3V, and you remain with just 100 GV. This is what we call fine tuning. You need to cancel some very large number, and you get out of this very small number. So you need B exactly to be 3AV plus 100. 3AV almost 10 to 12, 10 to 30 plus 100. So you can imagine as if you have 1, for example, and I wanted to tell you that, okay, add or subtract 0.001 plus or 1 dot 0.00001, you will get result of order 10 to minus something. This is what we mean by fine-tuning. So in order to avoid problem of proton decay from the triplet, you need to make this assumption and to split again, not only SU5, but most of the gut models. When you have when you have our standard model Higgs embedded in higher multiplets, you will have a problem with the higher component in this, because you want to keep our Higgs light, but the other components would be light the same light as a standard model Higgs, or this is danger, you want to push it up. So how to push it without pushing the standard model Higgs, and then you create what is known as a doublet triplet splitting problem. We already talked about the advantage, but let me summarize now that this is really this work of Georgia and Glashow was very successful to unify the electroweak and gauge strong interactions in one fundamental force, and in fact give the correct masses for W and Z. Unfortunately, not the good masses for the fermions, and it explained the charge quantization, as we said, why down sector is 1/3 and also up sector why 2/3 can be also seen. And in fact, all this explanation is completely out of scope of the standard model. The theory is renormalizable, and this is interesting. So it's calculable, it's nice, it's not as important. And it generalizes the standard model in most initiative, minimal, blah, elegant way. All this is matter of test of people. But now we have some disadvantage as well. It predicts proton decay and lepton number via the number from the triplet, and this is requires really some hard fine-tuning and some assumption. This particle cannot be predicted because it's quite heavy. So you end with just standard model particles. It has also another problem that it doesn't have right-handed neutrino from the construction. In this 5-bit and 10-bit, for that reason, I told you maybe you need to go to non-minimal SU5, and this is another issue, but something for work is open for non-minimal SU5 and supersymmetric SU5 as well. And in fact, hierarchy problem and splitting problem is an issue, and this is an unnatural difference. Masses, okay. We also, there is some issue about the weak mixing between W and Z, and also the skill dependent. Okay, this is, we didn't discuss the mixing, but this is some of the disadvantage. I think the last two is minor. The important really is the doublet and the hierarchy problems and the proton decay problem. Current status of the SU5. SU5, as I told you, is not completely dead, but it's known that we need to add something on top of the minimality of SU5. So non-minimal SU5 could be by including some, especially I'm quite interested about 45, and I did some work about 45 because it corrects the mass relations. It's Andrew Guy started it immediately after he discovered the bad mass relation obtained from SU5. He started to work SU5 with 45H. And but of course, the price we will pay 45. Can you imagine? The 24 is like that. 45 is 5 times 5 times 5. So it's, you cannot, this is like now you cannot write it. You can just work with indices and all this stuff. However, it works very well and solves the mass relation issue, but also it has a lot of elliptic quark triplets, triplet, doublet, not even triplet hypercharge like the one. But not all of them contribute to the proton decay. So you can push some of them to high scale who are contributing to proton decay, but the others who's not contributing to proton decay could be quite interested to have a kind of phenomena or signals or some process that require quark-lepton connections. And this is sometimes is useful and some anomaly appears nowadays. You can also adjoin, you can also put, instead of 45 or 5 heads, you can add some fermion, 24 the adjoint representation for the fermion. I told you the 24 could be scalar, vector, fermion, everything. And this is maybe, I think the 15F or 24F maybe is good for having something for right-handed neutrino. In fact, including supersymmetry to SU5, it helps a lot in the gauge coupling unification. It becomes 10 to 16 and hierarchy problems. And I'm not sure about SUSY SU5 if it solves the doublet triplet splitting or not. Shaib, do you remember when we add supersymmetry, doublet split experiment, doublet split not experiment, splitting problem will remain or supersymmetry? Is supersymmetry helps in avoiding the
No, it doesn't. We do
still fine-tuning? No, but without adding anything, it's just Susie, SU5. Still, we have doublet, triplet, splitting problem. Okay, because Susie usually help in solving the hierarchy, but hierarchy between 5 and 24, but 5 different component in 5, I'm not sure. Maybe most probably.
No, we did last year.
It wasn't Susie part, right? 2% depending. Okay. To conclude, with SU5 GOT was a big theoretical success, and it will always remain as an important playground for theorists seeking for unified models of nature, but maybe need some development, or maybe we consider something along this line, but not SU5, SO10. Next year, if we have a chance, we can discuss it. Okay, that's it, and thank you. And I finished, so I can open the floor, especially to people, only Murad, I think, and some other colleague here and online. So if they have questions, please go ahead.
No, I have just a simple question, a single question. I also hear about the model called flipped SU5. So, any idea?
It is SU5 times U1.
Oh, okay.
I didn't study too much, and I don't know what the extra U1 will do, but to my knowledge, it is mainly based on SU5 cross U1.
Okay.
The flipped SU5. Any other questions? Here they ask it more than, it seems not so simple like yesterday. It was more involved. So they already asked their questions. So if no questions online, then we are done essentially, and good, on time. But I cannot promise tomorrow will be on time because Susie will require, but I will not cover everything. I'll just highlight the main items. Okay, so see you tomorrow, guys, and bye-bye.
Okay, bye.
Bye.